Hello, everyone. We will wait a couple of minutes for everyone to join before we get started. Thank you. Okay, one more minute and we're going to start. Okay, I think we can start. Hello, everyone, and welcome to our new webinar about digital tomato, very interesting and requested topic. In this 45-minute pre-recorder session, we're going to talk about the opportunities for process improvement through IoT and digitalization in the food processing sector with our digital tomato, a CFT proactive asset monitoring tool for performance optimization. At the end of the presentation, we will have a Q&A session led by our Automation and Digitalization Director, Filippo Tedeschi. So please feel free to ask anytime, any question through our Q&A window located at the bottom of the Zoom meeting room. We thank you for taking the time to join us, and I hope you will enjoy. And I pass to Mario Gozzi, our America's Regional Sales Manager, to start the presentation. Thank you.
Thank you very much, Patricia, and welcome everyone. Today's webinar is about a journey that has just started, but it is already poised to open an unprecedented window of observation and comprehension on the overall process as we have never had before. It is just until yesterday, as many of you might know, that we were messing around with comma-separated values from the PLC, spending painful hours to get trends of single variable at a time and absolutely offline mode. The first real-time dashboards that are emerging from our first installations of the digital tomato are making those days look like the Middle Ages. The number of correlations and the deep understanding of the functioning of the machines that were allowed by the digital tomato are hard to imagine, and the savings achievable also in terms of cost are quite impressive. Just a note for your better comprehension of the presentation. It's divided basically into three parts. In the first one, we will give a general introduction of the digital tomato project on the whole processing line. The second part, we will show an insight of the first digital tomato installed at a North Italian customer this 2024 season, this last season. And this second part will be about the operator's dashboard. Third and final part, again, on the same North Italian customer, but in this case with the manager's dashboard, more oriented toward energy efficiency and yield improvement. We hope you enjoy the presentation, and we look forward for your question at the end of the session. Thank you very much. Enjoy.
Perfect. So let's get started introducing the digital tomato, proactive asset monitoring for performance optimization. With the final product price shrinking and the energy cost turmoil, as well as unpredictability of the climate condition and shorter seasons, The Digital Tomatoes performance optimization stands as an essential tool to keep your business competitive. The Digital Tomato is based on several tools. Here is a summary of the main ones. The first and most important one is the presence of edge devices and IoT. Basically installing sensors such as vibration monitoring or temperature control on all major pumps and actuators in order to have a predictive maintenance that will allow the customer to basically plan interventions and substituting a defective part before it actually fails, causing a major stop. The second point, the second tool is on-premise operator dashboards. A series of dashboards, as we will see in greater details, accessing key production metrics and equipment efficiency, starting from a very high level all the way down to single areas and single machine through dashboards, which are very intuitive and very synthetic, and this can be done anywhere 24/7. The third point is the cloud-based manager dashboard. Here we are providing a second level of analysis, which is not so much based on production metrics and productivity, but rather on efficiency, like extraction efficiency, transformation yields, and working cost. Fourth tool of this series is the subject matter expert access, basically the technician and the engineer behind the screen. Weekly performance reports, as well as final year strategic wrap-up meeting from fully dedicated subject matter expert. The Digital Tomato is built on pillars. When we first approached this project, it became evident that a tomato processing or as well as a strawberry processing line have hundreds of energetical streams getting in and out of it. And the risk was really to get a little bit lost and losing focus on the main goals. So we summarized into 5 pillars the major goals that we are tackling with the Digital Tomato. The first and one of the most important one is the extraction yield, transforming as much as possible of your valuable raw material into sellable final product. The second pillar is the evaporator balance for energy saving. What we mean here is that a modern line is typically built with an MVR folding film, such as an Apollo, concentrator for the 5 to 8.5 concentration, followed by eventually an Artemis in the 8.5 to 14 or 15 bricks, and finally a Venus triple effect. The balancing of these evaporators for achieving the best energy performance is something that is normally not included as an algorithm into the line, but something that would be very beneficial to have always the optimal configuration and save large portion of energy. Third pillar, equipment availability. It is quite often, unfortunately, in our industry where we have very short seasons to see large stops of the line due to a failure of a very minor component. Reducing those failures with predictive maintenance will allow us to improve by a few percentage points the overall availability of the line through the seasons. Fourth pillar is the final bricks accuracy. This is one of the most important points where most money and value can be saved. By not having a full control of the bricks, like for instance when I'm producing a 30-32 bricks, and eventually I'm targeting 31.2 to have a safety margin, what I'm doing is I'm giving away water, which I am extracting in the evaporator, that I could have sold as final sellable product. Fifth pillar is the product quality, correlating parameters such as the holding time and temperature into the hot breaks or the evaporator with the quality results, or even allowing, for instance, more green tomatoes through the optical sorters if I'm overshooting and I'm achieving a higher color than the one required by my final customer. In the extraction yield pillar, we are measuring equipment performances, such as the crushed tomatoes mass flow in, the waste humidity, which comes from the lab, whereas other parameters might come from the PLC, but that's totally perfect and normal. We're measuring the juice flow out and the motor power absorption. We are also acknowledging final customer product specifications in terms of finish, black specs, and so on. The current product quality. Through those values that we're measuring, we put in place actions like the automatic adjust of process parameters to optimize and keep the extraction yield at very high level. At this stage, many customers have asked the question, why should I do that with the digital tomato? What are the advantages that the digital tomato will bring? First of all, the digital tomato brings together data from different origins, notwithstanding whether it's the lab, the customer specs, or the equipment's PLC. Second advantage, it proactively and continuously chases extraction yield maximization with an eye on quality. Finally, it avoids human error. As regards the pillar number 2, the evaporator balance, we have summarized in these two slides how a traditional Venus triple effect works as compared to the more efficient MVR evaporators. Going from 0 to 100% of the water removal, which means on the bricks y-axis going from 5 to 28 bricks. If I'm processing and evaporating those tomatoes with a standard triple effect, I will be roughly in the range of 220 kWh per ton of water removal. If I'm doing the same job utilizing an MVR falling film evaporator followed by an MVR for circulation and leave only the last 20% to be managed with a triple effect, that's the situation I'm achieving where the light blue rectangle represents the energy saved. The digital tomato will balance out the functioning of the three evaporators to bring us as close as possible to this image we have on the right hand side. Equipment availability. What the digital tomato does, it records continuously critical parameters such as temperature, vibration, and presence of the lubricant in the most important pumps and actuators. It then compares the recorded data with allowable thresholds to identify misfunctioning and trigger preventive maintenance actions. Produces periodic accident and misfunctioning reports, and reduces the need for human detailed inspection, saving human resources. The image that you see below is relative to a misfortunate failure that we experienced during the last season at a South Hemisphere customer. Around March 28, one pump failed, and we could see from, in anticipation, from the vibrations that the pump was undergoing, that there had been an issue. Final bricks accuracy, definitely one of the most important points to be fixed as regards the value that it implies. And what we do here is we generate reduced waste and improve the transformation factor. We lower the energy consumption of the line, we generate improved margins, and finally we better match the final customer specification, easing his job in the final formulation, receiving a product which is more constant throughout the year. The chart below shows a typical fluctuation that was registered at a customer's plant during the production of a 3032 bricks. And it can be seen how the average bricks that was obtained was 31.18. So we were basically giving away nearly 1.18 bricks, overshooting with the concentration. The standard deviation in this case was 0.56 bricks. Product quality. We want to go from a fragmented data set from multiple sources to a cloud-based set of data, unified data management system where we can correlate the cause and effect. Like for instance, correlating the product temperature and the hold time in an evaporator with the effects that these parameters have on the color. Finally, as a result, improvements in product quality and potentially improving yield, like for instance allowing more green tomatoes when color specs will allow for it. The current status of most of the factory looks pretty much like this slide. So we have the data are there. The problem is they are scattered and hidden in a series of different streams. Like the laboratory is going to save its data on a paper sheet or in the best case on an Excel or ERP system. The receiving area will do the same, while we'll have several PLC recording data for each one of the equipment in the line. This is where we want to bring the factory, where all the input data are collected from a PC, a supervision PC, which is part of the supply. No matter where this data come from, it could be a lab, it could be a dump station, it could be a sampling station or an Apollo evaporator. We then shoot the data into the cloud through PA facts, and then at that stage we elaborate them. We might access some data from the steam tables or other sources, and we come out through algorithms with the feedback that adjust the processing parameters to maximize yield and energy savings. Okay, so let's get started and let's dive into this digital tomato application, which have been installed this year, 2024, in the North Hemisphere season for a North Italian customer. The very first screen that we see as we access the digital tomato, in this case, is an overview of the machines that are included under the supervision. The dashboard has been thought to reduce the amount of time and also the amount of information that the operator has to pay attention to. In this case, the operator can make faster decisions and monitor any deviation of the performance from the ideal condition. In the specific case, we have an Apollo MVR falling film evaporator and the Mixlo MVR forced circulation. The application is prepared to select here on the top other machines like the receiving, the hot break, the pulping finishing, or the concentration and aseptic filling when they will be present. What this screen shows is the operation mode, the prioritized alarms, and then the situation of the anomalies. It also shows the main variables of the line, such as the compressor speed or the flows. As we click on the Apollo MVR evaporator, we have a window on the right-hand side that pops up. The left-hand side basically reports back the same data I had from the previous level. And what I start seeing here is a series of information, like, for instance, we have widgets that are showing the average water removal here. In this case, the machine was designed for roughly 30,000 kg an hour. That's the nominal capacity is the light gray line. while with the white line we see the current evaporation capacity of the line, which is down to 14,870 kg an hour, so roughly 40% of the nominal capacity. The blue spot represents the set point that have been defined by the operator. Below that, we have the bricks, again as the current value and the target. The screen then goes on summarizing the two most important parameters concerning color, which are the A over B Hunter Lab color, red over yellow, which in this specific case was 1.93, over a set point or a target value of 190, and the Bostwick at 6.4 centimeters per 30 seconds. The chart then goes on showing the most important parameters related to the compressor. So in this case we have the compressor speed, 2056 RPM, fairly low revolution, which is compatible with the low water removal. And then we see the power, the total mechanical power absorbed by the unit, and how that is split in between the power that is transferred, or the energy that is transferred to the vapor, and the one that is lost for yield. In this specific case, due to the low velocity and to the low speed of the line, the yield of the compressor was down to 67.8%. Let me interrupt for a minute. All these things are a total novelty, and they were absolutely not present in any previous automation that CFT has done. So having the chance on the fly to take a look and visualize all these parameters is a fantastic window of opportunity indeed. We then have a look and we have a visibility on the vibration of the motor and the compressor. As we start picking these menus on the left-hand side, we get access to performance, quality, efficiency of the compressor, and vacuum and temperature. As we start with the performance, we have this chart on the upper left corner that shows us all the mass flow rate. So the mass flow in violet, the mass flow out, and as a difference, the water removal. We also get to see the bricks ratio, the ratio between the outgoing bricks and the incoming bricks. Whenever that value goes to 0, it means that I was experiencing some product recirculation in the plant. Finally, a very useful and quite inspiring Sankey chart of the mass flows, where I do see the fresh product to the line, the product being recirculated by the evaporator itself, and how that is transformed into water removal, delivered semi-concentrated product, mass that goes back in a recirculation loop, and a little quantity of uncondensables that come out of the system. The right-hand side part of the chart shows the total operative time. In this case, this specific machine has been operating for 46% of the time, had a 21% of equipment failure, which are alarms of any kind, and has been put in hold for 31% of the time. And it has been all this time in production mode, not CIP or not any other type of mode. The nice and interesting thing, again, from the Digital Tomato is correlation of the data, correlating the availability of the line with the most common alarms. And in this case, we see that the most common alarm in the Pareto list was the low bricks alarm. Density transmitter 500 was the one that gave the most of the alarm for 67% of the total time, followed by the second one, which has been the high level, so tailing back of product downstream the evaporator. Once again, this view was absolutely not present, and all the considerations that can derive from this view in terms of optimization can only be imagined. As we dive into the next menu, the menu regarding quality, again, these data were stored typically in the lab, pretty far away from the machinery control room, but now they're all managed in the cloud and brought to the at the disposal of the operator. So we can see Bostwick, color, and bricks taken in and the time where they were taken, and also what the reference value was. The color is currently at 1.93 over a target value of 1.93. On the right-hand side, we have an insight of the mass of product delivered to the plant and the holding time that we had through the line, combining the mass flow rate and the recirculation. Finally, on the bottom part of this quality slide, we have the standard deviation on the bricks. So in this case, we had an average value around 8 bricks, and the standard deviation was 0.14 bricks. We also get to see the minimum and maximum values that were recorded. Most importantly, the system correlates that deviation into percentage of product that have been lost. That has been called the product gift. So basically, in this particular case, we had roughly 3% of the production that have been lost, or tomato paste that have been transformed into evaporated water and sent to drain with zero value, just because we were not able to have a more precise bricks on the final product. We go now to the third menu, which is the one relative to the compressor performance. Also, in this case, very interesting relationships are established. Like, for instance, in the first chart, we see the MVR speed moving around 2,200 RPM, and the water removal that speed has generated. We can see that increasing the speed in the last portion of the period, this is an 8-hour period, the water removal increased consequently, as it should be. But most importantly, what we do see is also the yield of the compressor. That is the ratio of the energy which is absorbed by the fluid, in this case the vapor, divided by the energy that was absorbed by the motor. And we can see that this efficiency was fairly low at 60%, and only once we raised the speed of the compressor toward its nominal values, that efficiency was able to rise at 80% and above. What does a 60% efficiency mean? It means, in a very simple explanation, that out of 100 kilowatts you are purchasing from the electrical grid, only 60 kilowatts of those are transformed into compression of the vapors, and the other 40 kilowatts are lost. So it's a very important parameter. On the right-hand side, you see how that efficiency was generated, as we said at the beginning, simply with the relationship of the electrical energy absorbed by the motor of the compressor and its ratio with its relationship with the energy transferred to the steam, which is mass flow rate times the enthalpy gap. In the bottom left corner, we have the most common working points on a water removal to speed to RPM chart. And then finally, on the bottom right, we have the temperatures of the product coming inside the plant compared to the temperature of the vapors inside the separation chamber. Okay, so we're moving to the final part of the dashboard, the manager dashboard, which, as we said, is more dedicated to parameters such as working cost and yields. In the left part of the graphics, we see the production time, the utilization. In this case, 100% of the time was in production mode. In the central part of the chart, we see availability. So equipment was in operating condition at 88% of the time, 9% was equipment failure, and 2% all the time. On the right-hand part, we see the efficiency, so the machine was running at 53% of the nominal speed. We also see some totalizer on the bottom part of the screen summarizing the product delivered, product lost for inaccuracy of the bricks, roughly 25 tons in 3 days, and the total water removal. Even further down, we see totalizer on the energetic components, 2.2 tons of steam consumed, which are equivalent to 1.7 megawatt hour of energy, 31.7 megawatt electric megawatt consumed, and finally 5.8 thousand US euros of energy cost. In these graphics, we see the hourly production in tons per hour of the semi-concentrated juice, as well as the hourly water removal. We have to observe that this Apollo evaporator is roughly a 30 tons an hour unit machine, and here it was operating fairly below its nominal capacity and at a certain point in the neighborhood of 10 tons an hour of water removal. These charts are yet a slightly different visualization of the flow rates. So we have the product nominal flow rate to the plant, and we have the current flow rate of product is in blue color, and in red color we have the capacity that the machine could have had at the nominal speed, and we can see the gap between the two. In the upper one, we have the total water removal, and we can see that we were quite largely below 60% of the nominal capacity. Again, another view showing the daily capacity in water removal and the various flow as mass flow in, product outlet, and product bin recirculated. If we look at the compressor, we can see how the compressor speed was changing over time, trying to chase the correct bricks at the outlet. We can also see the efficiency of the compressor, the energetic efficiency of the compressor, which means the ratio between the energy delivered to the fluid, which is the vapor, and the energy absorbed by the electrical motor. Overall, the compressor had an efficiency of short of 73%. This other visualization allows us to see in a different way how we were in production mode for 100% of the period of 3 days, and where the various stops for equipment failure or voluntary hold in yellow or tailback happened during the production period. As regards the brick accuracy, we have a very interesting view. We can see exactly how the bricks fluctuated. Again, there are no modifications done here, no retrofits or algorithms, but just the monitoring of the as-is situation. The bricks had an average of 8.84, but we can see that it had quite some peaks of up to 1.2 and down to maybe 8.4 or something. As we look at the average of the standard deviation of the bricks from its set point, we can see how that value averaged 0.267 bricks. But we can also see that there were moments where this deviation is particularly high, up to 3.2 or 3.4 bricks. This we can quite easily correlate this event, for instance, to the recirculations. We can see quite easily, comparing the two charts, that when the machine had to recirculate on itself because of tailbacks or other issues, those were the moments where we most likely lost the control of the bricks. The system also calculates, and that's quite interesting synthetic value, the number of tons over the period that were lost or could not be sold due to inaccuracy in the bricks. So 25 tons could have been produced and sold, but were rather evaporated and discharged to the drain in form of evaporated water. As we look at energy, we can see that in this chart we have the steam consumption in blue color, the power, electrical power absorbed by the compressor in orange color, and the electrical power absorbed by other actuators in light yellow color. Once again, we can correlate these consumptions of steam to the moments where the machine was recirculating on itself, because those are the moments where the incoming flow of product becomes cold, not arriving anymore from the hot break but being recirculated, and those are the moments where a modulating valve has to transfer some makeup steam. In total, we had short of 32 megawatt-hour of electricity consumed and 1.7 megawatt-hour of thermal energy. Again, we have a view here of the total energy cost, which was 33,000 euros over the 3 days. And if we correlate that cost to the ton of product, the value that we have is 3.32. We can also correlate the energy cost to the ton of water removal if you prefer, and in that case it is 4.2 euros per ton of water. Here the digital tomato opens a very interesting window of comprehension, because we can see clearly how the cost of energy per ton of water removal was even up to 5 or 6 euros per ton, and as we were able to run the machine at a faster pace, closer to the nominal capacity, the energetic yield became much better, and thus the cost for tons of water removal went down quite remarkably. Very important for optimization of the working cost. Finally, these final charts show how a human intervention of the operators, by changing slightly some of the algorithms in the final part of the season, had a huge impact on productivity and energy saving. For instance, the MVR yield rose from 69 to 76% due to the modification on the controlling algorithms. Here you have to consider that 69%, what does it mean? It means that out of 100 kilowatts that you buy from the electrical network, only 69 of those are transferred to the vapor in forms of compression and enthalpy rise, and the rest are lost. 31 kilowatts out of 100 are lost into friction and inefficiencies. On the contrary, after the modification, up to 76%, 76 kilowatts out of 100, were transformed into compression. A similar result after the human intervention and after the subject matter expert was possible in the bricks accuracy, where the deviation went from 0.32 to 0.2. And if you make the math behind it, you realize there's quite some money involved or saved in this change. The last parameter on which we noticed the human intervention has been the specific cost of energy per ton of water removal. We went from values of 5.2 euros per ton of water removal of total energetic cost all the way down to 3.9 and even 3.8 euros per ton. So definitely a very remarkable and useful intervention that would have not been possible without all this visualization. As a conclusion, I would say that the digital tomato is really opening a fantastic window of observation and comprehension on the tomato processing line, as it has never been possible before. And even from the very first observation that we could carry out during this season, we realize of the enormous amount of interventions and optimizations that are possible. I think that we're still not understanding fully all the improvements that can be possible. We can only imagine those, but the start was really enthusiastic for us, and we're looking forward for further development. Thank you very much for your attention, and we look forward for all your questions.
Okay, so we hope you enjoyed the presentation. We're here this evening with our automation and digitalization manager, Filippo Tedeschi, which of course was the author and the brain behind much of this development on the digital tomato. And we'll take a look together at some of the questions that we received. So the first one, I'm going to read it out loud, was what are the next applications besides evaporators? I'll let Filippo answer on this one.
Yeah, as a next step, we are working to deploy a full plant digital tomato in a southern hemisphere. So we hope to be ready in January with a new use case with a full plant processing line.
Second question is about the cost structure of the digital tomato. Okay, so I'll take this. So basically, the structure that we have thought comprises an initial payment which covers for the sensors and actuators that are necessary on the line, the eyes and ears that we are currently missing on the line, as well as the central PC for centralization of the data and all the algorithms and software. All of that is covered from the initial down payment. And then there is another recurring fee that covers for the cloud storage, as well as for the subject matter expert supervision, its weekly reports and end of the year reporting, and as well covers for the news and novelties included in the next year's version of the software. The other question is about the values of potential savings. It is not easy to answer for all the customers. Of course, it depends a lot from the baseline. So because of that, in the initial assessment, we propose to draw a baseline from the last season, understanding what the yields in the extraction were and the energy costs were. And based on that, we can then guarantee the improvement and the parameters and come out with a value. Just for your reference, a recent analysis done for a fairly large factory, around 3,500 tons of tomato per day, led to a potential saving in the neighborhood of 900,000 euros per year. Next question is the steps a client needs to take to implement the digital tomato. I'll let Filippo on this.
Yes, as a first step, what we suggest is to do an assessment with our engineer in order to understand the status of the equipment and the availability of all the information that we need to calculate all the KPI that could be useful to monitor the performance. After that, we already understand we can prepare a list of instruments that we can add to your equipment, and then prepare an offer in order to start with the project.
Okay, so we have still maybe a minute available. There's a question here. I would also include among the monitored data the environmental parameters, ambient temperature, solar radiation, that may influence the transfer performance of the system, which is not thermally insulated toward the environment. That's a very good point. Since we are talking about efficiency, that could also be another very interesting point we have not thought of. So thanks for the observation. Every one of us which has been assisting the production during days and night shift know that there is a difference. So even the difference between day and night temperatures can cause quite a difference in performance. And so that might be a point very interesting to be monitored. Yet another one, I wonder if the recordings can be sent to my email for further analysis and assimilation. And point 2, can the MVR be linked with an existing evaporator process? And how is the saving with the reference to the data collection be accurate? So the fact about sending to the email, I'll let Filippo answer this.
Yeah, the data will be available through the dashboard and could be exported in Excel file or in different formats. So it could be available to make different and further analysis also out of the system.
Yeah, the second part of the question was relating to the whether or not MVR could be linked to an MVR are typically purchased either as a concentrator for achieving a semi-concentrated product like a passata, for instance, at 8.5 bricks, but it can also work as a pre-concentrator for existing evaporators, and could also be possible to retrofit MVR on an existing evaporator. The final part, how is the saving with reference to the accuracy of data collection? I'm not sure if I understand it, but the data we collect, of course, are fairly accurate. Of course, there is a topic that we were discussing in the past days about the accuracy of the instruments. So the accuracy of the instruments being comparable to the accuracy that we want to achieve. I don't know if you want to spend a couple of words on that.
Of course, the accuracy of the instrument could affect or could influence the data, but for sure the visibility that could give to us and to the customer this system with all this data could give a very good benefit to the customer in order of saving.
Okay, I see maybe one just last question. It is about the PLC and is asking whether Siemens or Omron have an influence on the possibility of integrating the digital tomato in a system.
Yes, it could be during the assessment we have to evaluate what could be the modification that the equipment needs, because we must be sure that all the information it will be available in the PLC. So during the assessment we can understand if it's not related to the brand of the PLC, but it's more related to the availability of the information that we need.
Yeah, I will only add that a previous question we have received, a similar one, was asking whether or not machineries from different OEM could be integrated, and the answer is yes. We can integrate machineries from CFT as well as from other vendors, and as well as all the data coming from the labs and dumping station and so on. Okay, I think we've gone through all the questions for the time being. We thank you again very much for your time and for asking all these questions. And we, of course, the whole team remains available and at your disposal for further information. I just remind everybody that the next webinar is going to be October 30th, and it's going to be specifically on MVR evaporators and the nice and interesting saving they can bring. And the last thing that you will receive the survey at the end of this webinar relative to your opinions. We thank you so very much again and hope you have a wonderful evening. Bye-bye.
Okay.